You're falling, right now, through a hole in space 2 billion light-years wide. Scientists confirmed this in 2013. You weren't told. This emptiness is warping every measurement we make about reality itself. The universe appears to expand faster here than anywhere else, breaking our most fundamental equations. We're about to journey through the discovery that shattered cosmology, explore why 90% of space is hollow, and reveal what it means to exist in the cosmic outskirts. 3 astronomers counted galaxies and found something impossible, 20% fewer than there should be. The pattern stretched outward in every direction for a billion light-years, forming a sphere of cosmic emptiness with us near the center. The statistical probability of this? Less than 1 in 1,000. Some scientists calculated it would take a 10 sigma deviation from average density, so unlikely you might not find one in the entire observable universe. Yet here we are, living inside one. But before we dive deeper, let me show you exactly how they discovered this. Picture this: 3 researchers staring at computer screens in 2013. Ryan Keenan examines the data from 35,000 galaxies. His eyes narrow. He runs the calculation again. Same result. Amy Barger checks using a completely different survey. She gets the same numbers. Lennox Cowie approaches it from a third angle. The answer doesn't change. Everywhere they looked near Earth, galaxies were missing, 20% fewer than cosmology predicted. They triple-checked everything, used multiple galaxy surveys, examined the sky from different angles. The result remained consistent. Our galaxy and everything around it sits inside an underdense bubble of space so massive it dwarfs everything else we've ever observed. They called it the KBC void, using their initials. Sounds casual, right? There's nothing casual about what it represents. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together and leave empty spaces between them. That's expected. But a region this enormous, with such a significant deficit of matter, pushes the boundaries of what random chance can explain. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this large and this empty. When they do, it requires exceptionally rare initial conditions. Think about what this means for a second. The implications began cascading immediately. If we reside in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to measure how fast the universe expands, are we seeing the true cosmic expansion rate or a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, the Hubble tension. For years, scientists have measured 2 different expansion rates depending on whether they look at the ancient universe or the nearby universe. The numbers disagree by 9%. Sounds small, but it represents a crisis. Both measurements are incredibly precise. Both should give the same answer. They don't. If Earth sits inside a massive underdense region, gravity from the denser matter surrounding the void would pull outward on galaxies within it. That would add extra velocity to their motion away from us, making the local expansion appear faster than average. Suddenly, the conflicting measurements made sense. We're measuring it from inside a hole. This realization changed everything, but it also raised an uncomfortable question that cosmologists are still grappling with today. If our location is this unusual, can we trust anything we think we know about the cosmos? What comes next reveals just how strange our cosmic neighborhood really is. Cosmic voids are actually far stranger than their name suggests. When astronomers call a region a void, they mean it contains far less matter than average. But matter still exists there. The void around us has roughly 15% of the normal cosmic density. Picture it this way. If a typical region of space has 10 galaxies in a given volume, the same volume in our void might have only 1 or 2. The galaxies don't vanish completely. They become rare, scattered islands in an ocean of near-nothingness. Between these lonely galaxies stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. No new galaxy clusters can form. No rich superclusters emerge. The void stays a void. This emptiness has consequences that ripple through physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant. The dominant force becomes dark energy, the mysterious pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down the expansion in those areas. Inside voids, gravity loses that tug of war. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes. which allows even faster expansion. Scientists confirmed this through careful observation. They measured how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls downhill from the mountains toward the valley. But since we're talking about space rather than terrain, that pull makes galaxies fall outward, away from the center. The effect is measurable and significant. Our own galaxy is moving away from the local void at 600,000 miles per hour. Driven by this gravitational imbalance, the interior of a void becomes a strange place for physics. Light travels through it, experiencing less gravitational influence than light passing through normal space. This affects observations in subtle ways. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity in voids causes less gravitational redshift, showing up as cold spots in temperature maps of the early universe. These cold spots line up perfectly with where we observe large voids today. This alignment isn't coincidence, it's physics. Understanding what makes voids empty helps explain why they matter so much to cosmology. They're laboratories where dark energy dominates and where gravity takes a back seat. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works. The KBC void around us might be unsettling because it makes us question our cosmic typicality, but it also offers a rare opportunity. We're positioned in exactly the right place to study the universe's most extreme low-density environments. The structure that contains these voids is far stranger than anyone imagined. The universe resembles Swiss cheese, where dense matter forms walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density. These nodes shine brilliantly with millions of galaxies packed relatively close together. Stretching between them run filaments, long chains of galaxy groups that can extend for hundreds of millions of light years. These filaments form walls, vast sheets where galaxies gather in higher than average concentrations. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. This structure wasn't always obvious. For decades, astronomers photographed the sky and counted galaxies, but the true three-dimensional arrangement remained hidden. Distance measurements were poor. Galaxies that appeared next to each other might actually be separated by billions of light years, with one much farther away than the other. Only when scientists began measuring galaxy redshifts systematically in the 1970s and 80s did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution snapped into focus. The universe had structure on scales nobody expected. The first major void discovery came in 1978, when two independent teams identified large, underdense regions. More surveys followed, each mapping deeper into space and revealing an increasingly intricate web. The Sloan Digital Sky Survey, which began in 2000, created spectacular three-dimensional maps spanning billions of light years. These maps show the cosmic web in stunning detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light years across. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light years long. On the opposite end of the spectrum, supervoids like the Eridanus void stretch 1.8 billion light-years wide, with even fewer galaxies than the KBC void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted. Galaxies aren't the fundamental building blocks. The web itself is the structure, with galaxies just marking where the matter happens to concentrate. Why does the universe organize this way? The answer reaches back to the beginning. Immediately after the Big Bang, matter wasn't perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density. Some regions were slightly denser than average, others slightly less dense. These differences were minuscule, maybe 1 part in 100,000, but gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile, the underdense regions expanded into voids. The cosmic web is essentially gravity doing its work over cosmic time, turning barely noticeable initial ripples into the grandest architecture in existence. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. This imbalance defines the universe's character. We live in a cosmos of emptiness punctuated by occasional concentrations of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble, and that makes all the difference for what we observe and how we interpret the universe. The Milky Way sits somewhere between 200 and 400 million light-years from the void's actual center. That might sound like a huge distance, and it is compared to anything humans experience. But the void extends outward for 1 billion light-years in every direction from its center, making our offset relatively small. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. This position has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely, in one of the dense filaments, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension would not exist. Our larger cosmic neighborhood adds another layer to this story. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbor Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any normal standard, yet even this supercluster resides within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. The void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population of matter scattered through the void, one of the rare concentrations in an otherwise barren expanse. The local group is also influenced by another nearby void called the local void, which is distinct from but connected to the larger KBC void. The local void extends about 200 million light-years and sits adjacent to our position. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond. This motion is separate from the overall cosmic expansion. It's a peculiar velocity, meaning it results from local gravitational effects rather than the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate because they add extra motion on top of the expansion signal. Astronomers must carefully account for these local effects, but inside a supervoid, those effects are amplified and harder to separate cleanly. The void's influence reaches even farther. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that exceed predictions from standard cosmology. Entire regions of space are moving faster than they should be, flowing in coherent patterns driven by the void's gravitational imbalance. The KBC void creates a large-scale velocity field that affects everything within it. Galaxies aren't just sitting in an empty region passively expanding with the universe. They're actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. This makes our local patch of the universe more dynamic and unusual than the calm, uniform cosmos that standard models assume. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. That light experiences less gravitational interaction than light traveling through denser regions. The reduced gravity creates subtle effects on the light's wavelength and energy. Additionally, the void itself influences the distribution of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range. Beyond the shell, the universe returns to more typical density. This creates an observational bias. We're sampling from inside one of its most extreme features. Living in the void means living with systematic uncertainty about how typical our measurements really are. Every measurement you've ever heard about the universe's expansion rate might be skewed by our location. The problem reveals itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space expands. One method looks at the cosmic microwave background, ancient light from when the universe was just 380,000 years old. This light encodes information about the early universe's density and expansion rate. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.3 million light-years, space expands at 67 kilometers per second. The second method looks at nearby objects with known brightness, specifically type Ia supernovae and Cepheids variable stars. stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing their actual brightness to their apparent brightness as seen from Earth, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise with very small error margins. Both should give the same answer if cosmology is correct. They don't. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there's less than a 1 in a million chance. It's just random variation. The KBC void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we're measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region. This inflates the local Hubble constant measurement. We're measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. But here's where it gets uncomfortable. If the void explains our local measurements, then those measurements don't tell us about the universe as a whole. They tell us about our weird local environment. The cosmic microwave background method is unaffected by the void because it probes the early universe long before voids formed. That measurement might be the accurate one for the universe's global properties. This means most headlines you've seen about the accelerating universe and dark energy might be describing a local phenomenon rather than a universal truth. We've spent decades building cosmological models based partly on local expansion measurements, and those measurements might be systematically biased by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special location. The principle states that the universe should look roughly the same from any vantage point once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. It suggests we're in an unusual location, which makes physicists uncomfortable. Science has progressively decentered humanity from special cosmic positions. Earth isn't the center of the solar system. The solar system isn't the center of the galaxy. The galaxy isn't the center of anything. And now we're supposed to believe we just happen to live inside one of the largest voids ever observed. The statistical improbability bothers many researchers, yet the evidence keeps mounting. The void exists. Our measurements are discrepant. The void's effects match the observations. Whether we like the implications or not, the universe might actually be distorting what we measure based on our location, or more precisely, our location is causing us to misinterpret what we observe. The crisis this creates in cosmology runs deeper than most people realize. The Hubble tension represents a fundamental challenge to our understanding of cosmic evolution. Cosmology rests on a framework called lambda cold dark matter, or the standard model of cosmology. This model has been spectacularly successful at explaining observations from multiple sources. It accounts for the cosmic microwave background temperature fluctuations, the abundance of light elements like hydrogen and helium, the formation of galaxies, and the large-scale structure of the universe. For decades, it has been the consensus model because it works so well in so many contexts. But the Hubble tension suggests something is missing or wrong in this framework. When a model's predictions disagree with observations at the 5 sigma level, scientists must take that seriously. The tension matters because the expansion rate determines everything else about cosmic history. If the universe expands faster, it reaches its current size in less time, making the universe younger. Current calculations based on the cosmic microwave background put the universe's age at 13.8 billion years. But if the higher local measurement is correct globally, the universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters that appear to be 13 billion years old, based on stellar evolution models. These stars would be older than the universe itself, which is impossible. Either our age measurements for stars are wrong, our understanding of stellar physics is wrong, or the higher Hubble constant does not apply to the early universe. None of these options are comfortable. The tension also affects our understanding of dark energy, the mysterious force accelerating cosmic expansion. Dark energy makes up about 68% of the universe's total energy content, according to standard models, but its properties depend sensitively on the expansion rate. rate. If the expansion rate is higher than we thought, dark energy's behavior might be different than current models assume. Some researchers have proposed that dark energy evolves over time rather than being constant, which would be revolutionary. Others suggest we need to add new physics to the early universe, perhaps an extra burst of accelerated expansion shortly after the Big Bang. Every proposed solution introduces new complications and requires evidence beyond just fixing the Hubble tension. Dozens of alternative explanations have been put forward. Some scientists propose that the measurements themselves contain subtle systematic errors that have been overlooked. Perhaps dust between galaxies dims supernovae more than accounted for, making them appear farther away and inflating the expansion rate. Or maybe Cepheid variable stars behave differently in different environments, biasing their use as distance indicators. These explanations keep getting tested and ruled out as measurement techniques improve. The measurements are solid. Other researchers suggest modifications to general relativity, Einstein's theory of gravity. Maybe gravity works slightly differently on cosmological scales than we think, which would change predictions for expansion. This route leads into controversial territory because general relativity has passed every other test thrown at it. The void hypothesis offers a cleaner solution that requires less modification to fundamental physics. It simply states that we're in an unusual location, and our local measurements reflect that rather than reflecting universal properties. This explanation bothers people philosophically, but requires fewer assumptions than inventing new particles or changing gravity. Recent work has strengthened the void hypothesis by showing it naturally predicts other observations. For example, the outflow velocity from the void should affect the expansion rate and also the motion of galaxy clusters in our vicinity. Measurements of these bulk flows match the void predictions. The hypothesis is making testable predictions that are being confirmed. Nevertheless, debate continues. Some argue that even a void as large as the KBC cannot produce a big enough effect to fully explain the tension. Others point out that supervoids this large should be rare, and finding ourselves in one just when we develop the precision to measure the Hubble constant seems suspicious. Maybe we're interpreting the data incorrectly somehow. The controversy remains unresolved, which is why the Hubble tension continues to be called a crisis in cosmology. Understanding how gravity creates this situation requires looking at how forces work in empty space. Gravity inside a void does something counterintuitive. It appears to push outward instead of pulling inward. The force of gravity always attracts mass toward mass, but the geometry matters enormously. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means pulling you away from the valley center. Inside a cosmic void, galaxies experience the same effect. All the matter lies outside the void in the surrounding filaments and clusters. That exterior matter gravitationally attracts the interior material, pulling galaxies outward from the void center toward the denser regions beyond. The result is an outflow, a systematic pattern of galaxies accelerating away from the underdense region. This outflow is measurable and significant. Astronomers can track galaxy velocities using redshift measurements combined with distance estimates. When they map velocities around known voids, the pattern is clear. Galaxies near void centers are moving faster outward than cosmic expansion alone predicts. The effect is strongest near the void center and weakens toward the edges where matter density increases. For the KBC void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. Our own galaxy participates in this pattern. The Milky Way is moving at 600,000 miles per hour away from the nearby local void, driven by the gravitational imbalance. This motion combines with other local effects, like the gravitational pull from the Virgo cluster, to create our galaxy's overall peculiar velocity. The outflow has implications for cosmic expansion measurements. When we observe distant galaxies and measure their redshift, we're seeing a combination of two effects: the expansion of space itself and the peculiar motion of galaxies due to gravity. Normally, scientists can separate these components because peculiar velocities average out when you look at large enough volumes. For every galaxy moving toward you due to local gravity, another galaxy is moving away, and the average is zero. But inside a void, the peculiar velocities don't average out. They all point in the same direction, outward. This creates a systematic bias that inflates the apparent expansion rate when measured from within the void. The problem compounds at different distance scales. Close to the void center, the outflow is rapid. Farther from the center, but still within the void, the outflow is slower. Beyond the void's edge, the peculiar velocities might even reverse as matter falls back toward the denser filaments. This creates a complicated velocity profile that varies with distance. When astronomers measure the Hubble constant using supernovae at different distances, they're sampling this varying velocity field. If most of their supernovae lie within the void, which they do because we deliberately avoid using extremely distant supernovae due to other complications, the measurement gets boosted by the outflow. The farther out you measure, the less the void affects the result. This predicts that the Hubble constant should appear to decrease with distance, and recent observations confirm exactly that trend. Modeling these effects requires careful calculation. Scientists must estimate the void's size, depth, and density profile, then calculate the gravitational potential it creates. That potential determines how fast material flows outward at each radius. The calculations show that a void roughly 1 billion light-years in radius with a 20% density deficit can easily produce the observed velocity anomalies. The match between predictions and observations is good enough that many researchers find the void explanation compelling. However, the standard cosmological model struggles to explain how such a large void formed in the first place. Computer simulations based on lambda cold dark matter rarely produce voids this extreme. When they do, it requires very specific initial conditions that are statistically unlikely. This raises a troubling possibility. Maybe our cosmological model is missing something. If voids larger and deeper than expected keep showing up in observations, perhaps structure formation works differently than standard theory predicts. Some scientists propose modified gravity theories where gravity is stronger on large scales, which would enhance structure formation and make big voids more common. Others suggest that the universe is simply more inhomogeneous than assumed, which would also make large voids less surprising. Either way, the backwards gravity in voids is telling us something important about cosmic evolution. Our motion through this gravitational landscape is faster than anyone expected. The Milky Way plummets through the cosmos at 600,000 miles per hour, roughly 850 times the speed of sound. This velocity comes from local gravitational effects. Specifically, our galaxy is being pulled away from the local void and toward the denser structures beyond it. The local void is distinct from but connected to the larger KBC void, and it exerts a strong influence on our motion. The void itself doesn't push us. Rather, the deficit of matter in the void means there's less gravity pulling us toward it compared to the gravity pulling us in other directions. The denser regions win the tug of war, accelerating our galaxy away from the underdensity. This speed is difficult to comprehend. 600,000 miles per hour means the Milky Way travels about 167 miles every second. In a single year, our galaxy moves about 5.2 billion miles through space relative to the void. But even at this breakneck pace, the void is so vast that our motion barely makes a dent. It would take hundreds of millions of years to cross from one side of the void to the other. Even at this speed, meanwhile, the void continues expanding due to cosmic expansion and dark energy, growing faster than we can escape it. We're inside the void now, and we will remain inside it for the foreseeable cosmic future. The local sheet adds another component to our motion. The local sheet is a flattened structure of galaxies that includes the Milky Way, Andromeda, and other nearby galaxies. This sheet forms one wall of the local void. The entire sheet is rushing away from the void center at about 260 kilometers per second, which is roughly 580,000 miles per hour. Our galaxy participates in this bulk motion along with its neighbors. The sheet isn't static, it's actively being evacuated from the void region, flowing outward like water draining from a depression. This motion has been ongoing for billions of years and will continue for billions more. But there's more to our velocity than just escaping the void. The Milky Way is also falling toward the Virgo cluster, a rich concentration of galaxies about 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and has enough mass to gravitationally attract everything in the surrounding region, including us. This adds another component to our peculiar velocity, roughly 250 kilometers per second directed toward Virgo. Meanwhile, the Milky Way and Andromeda are falling toward each other and will collide in about 4 billion years. That motion adds yet another velocity component. When you add up all these gravitational influences, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame is about 627 kilometers per second. That's the velocity astronomers measure when they look at the dipole pattern in the cosmic microwave background temperature. These motions matter because they complicate cosmological measurements. When we observe distant galaxies and measure their redshift, we need to correct for our own motion through space. Otherwise, galaxies in the direction we're moving appear blue-shifted, and galaxies in the opposite direction appear red-shifted, creating a false pattern that mimics cosmic structure. Astronomers have known about these corrections for decades and routinely apply them. But inside a void, the corrections become more complicated because the void itself creates large-scale bulk flows that extend over hundreds of millions of light-years. Disentangling the void effect from the true cosmic expansion requires careful modeling of the local velocity field. Our high speed through space is itself evidence for the void. If we lived in a typical region with average density, our peculiar velocity would be much smaller, maybe 100 or 200 kilometers per second at most. The fact that we're moving so fast indicates strong gravitational gradients in our vicinity, exactly what you would expect from being near a large, underdense region. The velocity is consistent with the void hypothesis. limitless and would be difficult to explain without it. This makes our motion a key piece of evidence in the debate over whether the KBC void exists and whether it affects our measurements. The universe may be distorting our perception of its expansion rate based on location, but it cannot hide the fact that we're racing through it at incredible speed. This motion connects to a deeper principle that the void fundamentally violates. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to shatter it. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special or different from any other when you average over large regions. Isotropic means the same in all directions. The universe looks the same no matter which way you look. These assumptions simplify the mathematics of cosmology enormously. They allow scientists to model the entire universe using relatively straightforward equations. Without the cosmological principle, the equations become vastly more complicated and predictions become much harder to make. The principle has been remarkably successful, accurately describing many observations, but the KBC void represents a major violation of homogeneity. If the void is 2 billion light-years across with a 20% density deficit, that's a huge inhomogeneity. Even on cosmic scales, the void is substantial compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling, we happen to live near the center of this abnormal structure, which seems to contradict the idea that our location is unremarkable. Throughout history, science has progressively removed Earth from any special position. Copernicus showed Earth wasn't the center of the solar system. Later observations showed the solar system wasn't the center of the galaxy, and the galaxy wasn't the center of anything. The cosmological principle is the ultimate expression of this trend. Earth isn't at the center because there is no center. Every location is equivalent. The void challenges that worldview. If we live inside an abnormally large, underdense region, our location is unusual by definition. Voids are common in the universe, but most are smaller than the KBC void. Supervoids this large are rare. Finding ourselves in one raises questions about whether the cosmological principle truly holds, or whether it's only approximately true on scales much larger than previously thought. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare, perhaps a 10 sigma statistical deviation. In a typical random realization of the universe's structure, you might not find one anywhere in the observable cosmos, yet we're in one. This suggests either we're incredibly lucky or the standard model is wrong about how structure forms. Defenders of the cosmological principle argue that the void doesn't actually violate the principle because homogeneity only applies at scales of several hundred megaparsecs or larger. The void is about 600 megaparsecs across, which is right at the edge of where homogeneity is supposed to kick in. Maybe the universe is less smooth at those scales than we assumed. Alternatively, maybe the void isn't as extreme as measurements suggest. Different observational techniques give somewhat different density contrasts for the void. If the true deficit is closer to 10 or 15% rather than 20, the statistical rarity becomes less severe. These counterarguments preserve the cosmological principle, but require accepting that our measurements are less precise than we thought. Another defense is that we shouldn't be surprised to find ourselves in an unusual location because observers can only exist in certain types of environments. This is a weak anthropic argument. Perhaps intelligent life requires galaxies to form, and galaxies form preferentially in moderately dense regions rather than in the densest clusters or the emptiest voids. If most observers live in mildly underdense regions, then finding ourselves in a slight void wouldn't be surprising. But this argument only works if the KBC void isn't as extreme as it appears. A 20% deficit is more than mild. It pushes the boundary of what the anthropic principle can explain away. The debate over the cosmological principle remains unsettled. Some researchers believe the void is real and significant, requiring either modifications to cosmology or acceptance that Earth occupies a genuinely unusual position. Others believe the void is an observational artifact or less extreme than initially reported. Still others propose that the principle holds on even larger scales and that the apparent violation is temporary. Future observations should help resolve this. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict or whether they're more common than expected. If big voids turn out to be frequent, the cosmological principle survives, but the standard model needs revision. If they're truly rare, we need to explain why we happen to live in one. The origin of these voids reaches back to the universe's first moments. The voids we observe today began as infinitesimal quantum ripples in the first moments after the Big Bang. During a period called inflation, the universe expanded exponentially for a tiny fraction of a second, perhaps 10 to the minus 35 seconds. During this expansion, quantum fluctuations were stretched from subatomic scales to cosmic scales. These fluctuations created slight variations in the density of matter and energy. In some regions, density was a tiny bit higher than average. In others, it was a tiny bit lower. The variations were incredibly small, about 1 part in 100,000, but they were enough to set the stage for everything that followed. After inflation ended, the universe continued expanding, but at a much slower rate. Matter began to clump together under gravity, and gravitational pulling only amplified the initial density differences. Regions that started slightly denser attracted more matter from their surroundings, making them denser still. This created a positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters of galaxies. Meanwhile, regions that started slightly less dense lost matter to their denser neighbors. As matter drained away toward the collapsing overdense regions, the underdense regions became even emptier. These underdense regions evolved into voids. The process is called gravitational instability, and it turned barely perceptible initial ripples into the dramatic large-scale structure we observe today. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was only 380,000 years old. At that time, the variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree. But those temperature differences correspond directly to density differences. Warmer spots had slightly higher density, cooler spots had slightly lower density. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped these temperature variations in exquisite detail across the entire sky. The maps show a mottled pattern of hot and cold spots at various angular scales. This pattern encodes the seeds of structure formation. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe. The match between predictions and observations is one of the great successes of modern cosmology. It confirms that our understanding of how gravity shapes structure over cosmic time is largely correct. However, the simulations rarely produce voids as large or as deep as the KBC void. This is where tension arises. The initial quantum fluctuations were random, so every region had some chance of ending up as a void or a filament. But probability distributions matter. Small voids should be common. Medium voids should be less common. Extremely large voids should be very rare. The KBC void appears to fall into the extremely rare category, which raises questions about whether our simulations are missing something. One possibility is that the initial quantum fluctuations weren't completely random but had subtle patterns that enhanced the formation of large voids. This could happen if inflation didn't smooth out structure as uniformly as standard models assume. Another possibility is that gravity works slightly differently on large scales than general relativity predicts, which would change how voids form and evolve. A third option is that the universe simply has more variance in structure than cosmologists expected, making large voids less surprising. Each of these explanations requires further evidence. Observations of more distant voids in other parts of the universe would help determine how rare the KBC void truly is. If similar voids turn up frequently, it suggests the standard model underestimates structure variance. If they remain exceedingly rare, it strengthens the case for modified physics or unusual initial conditions. The quantum origin of voids is both elegant and unsettling. It means that the cosmic desert we inhabit traces back to subatomic processes that occurred before atoms even existed. Randomness at the smallest scales propagated upward to create structure at the largest scales. The universe's organization wasn't designed or predetermined. It's the consequence of random quantum fluctuations amplified by gravity over billions of years. This realization is one of the profound insights of modern cosmology, but it also means that our location within this structure is the result of chance. There's no reason we had to end up in a void rather than in a filament. We're here because the initial conditions in our region happened to be slightly underdense. That accident of quantum chance 14 billion years ago determines what we observe when we look out at the cosmos today. The scale of these empty regions dwarfs human imagination. When you picture the universe, you probably imagine a sky full of stars and galaxies. But the reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids. This isn't just empty space in the sense of vacuum between stars. It's empty in the sense that entire regions, hundreds of millions of light years across, contain almost no galaxies at all. If you could travel through a void, You would fly for tens of millions of years at the speed of light without encountering a single galaxy. The isolation would be nearly absolute. This distribution creates a lopsided universe. Most of the matter concentrates in a small fraction of the volume. The filaments are crowded with galaxies that interact, merge, and evolve rapidly. Star formation is vigorous. Black holes grow, galaxies collide and trigger bursts of star creation. Meanwhile, the voids are quiet. A few lonely dwarf galaxies drift through the darkness, separated by vast distances. These void galaxies evolve slowly because they rarely interact with neighbors. They tend to be smaller, fainter, and less evolved than galaxies in dense regions. Star formation is sluggish. Many void galaxies contain large amounts of neutral hydrogen gas that hasn't yet condensed into stars. They're galactic backwaters, isolated from the busy highways of the cosmic web. The extreme emptiness of voids raises questions about how empty space can really be. Even in voids, dark matter is present. Dark matter makes up about 85% of all matter in the universe, but doesn't interact with light, making it invisible to telescopes. It's detectable only through its gravitational effect. In voids, dark matter is much less concentrated than in filaments, but it still exists at about 15% of the cosmic average density. That might sound like a lot, but spread over such huge volumes, the amount of dark matter per cubic light-year is incredibly tiny. Additionally, voids contain dark energy, the mysterious component driving cosmic acceleration. Dark energy appears to be uniform throughout space, so voids have just as much dark energy per volume as dense regions. In fact, because dark energy doesn't clump like matter, it becomes the dominant component in voids where matter is scarce. The interplay between dark matter and dark energy determines void evolution. In the early universe, matter dominated even in underdense regions, and gravity still mattered. As the universe expanded and dark energy became more important, voids began accelerating their expansion. This acceleration makes voids grow faster over time, eating into the surrounding filaments. Eventually, if dark energy continues to dominate, voids will consume more and more of the universe. Filaments will thin out. Galaxy clusters will become isolated islands in an ever-expanding ocean of nothingness. This future is billions of years away, but the process has already begun. The voids we observe today are larger now than they were a billion years ago. They'll be even larger a billion years from now. The cosmic web is being slowly stretched and torn apart by the accelerating expansion driven by dark energy. Understanding this process requires understanding dark energy itself, which remains one of the biggest mysteries in physics. We know it exists because we observe its effects. The expansion of the universe is accelerating, and that acceleration requires some form of energy with negative pressure. We call it dark energy, but we don't really know what it is. The simplest explanation is that dark energy is the vacuum energy of space itself, a property inherent to empty space. Quantum field theory predicts that even empty space should have energy due to quantum fluctuations. But when physicists calculate how much vacuum energy there should be, they get a number that's 10 to the 120th power larger than what we observe. That's a factor of 1 followed by 120 zeros. It's the worst prediction in the history of science. Something is clearly wrong with our understanding, but we don't know what. Alternative explanations for dark energy include a new type of field permeating space, modifications to gravity on cosmological scales, or even the possibility that we're misinterpreting the observations entirely. Each explanation has problems, and none has been definitively confirmed or ruled out. The KBC void adds another layer of complexity to this mystery. If the void affects our measurements of the expansion rate, it also affects our inferences about dark energy. The amount and properties of dark energy we calculate depend on the expansion rate we measure. If that measurement is biased by our location in a void, our understanding of dark energy might be skewed as well. Some researchers have proposed that what we call dark energy might actually be a local effect related to the void structure around us, rather than a universal property of space. This is a radical idea that most cosmologists don't accept, but it illustrates how uncertain our understanding remains. The void forces us to question assumptions we've taken for granted for decades. One way to test these ideas is to look for other large voids and see if regions near them show similar patterns in expansion measurements. If every large void creates a local enhancement of the apparent expansion rate, that would strongly support the void hypothesis. If large voids don't consistently produce this effect, it would suggest something else is going on. Another approach is to use different traces of structure to map the void more precisely. Galaxies are the most obvious traces, but we can also look at the distribution of neutral hydrogen gas, the cosmic microwave background, and even gravitational lensing effects. Each method provides independent information about where matter is and isn't. Recent studies using multiple tracers have generally confirmed that the KBC void exists and has roughly the properties initially reported. But there's still debate about exactly how deep it is and whether its edges are as sharp as some models suggest. These details matter because they affect the predictions for how much the void should influence local measurements. There's also the question of whether other large voids exist that we haven't discovered yet. The universe is vast, and we've only mapped a small fraction of it in detail. Deeper surveys that reach farther into space might reveal more supervoids, which would help us understand how common they really are. If they're everywhere, the cosmological principle is safe, and we just need to update our models. If they're genuinely rare, we face deeper questions about why we're in one. The implications extend beyond cosmology. If our location in a void significantly affects what we observe, it means that any civilization anywhere in the universe would need to account for their local environment when trying to understand the cosmos. A civilization in a dense cluster would measure different things than a civilization in a void. Neither would be wrong, but both would need to recognize that their local perspective doesn't necessarily reflect universal truths. This raises philosophical questions about the nature of scientific knowledge. We pride ourselves on discovering universal laws that apply everywhere and everywhen. But if our observations are fundamentally colored by where we happen to be, how can we be sure we're seeing the universe as it truly is? The answer is that we can't be completely sure. We can only try to account for local effects as best we can, and hope that our models are accurate enough. The good news is that we have ways to test the void hypothesis and distinguish it from alternatives. The next decade will be crucial for resolving these questions. Several major observational programs are underway or planned that will provide the data we need to either confirm the void explanation or rule it out. One key test involves measuring something called baryon acoustic oscillations. These are subtle patterns in the distribution of galaxies that formed in the early universe, like ripples frozen into the cosmic structure. The size of these patterns depends on cosmological parameters, including the expansion rate. By measuring baryon acoustic oscillations at different distances, astronomers can trace how the expansion rate changes with both distance and direction. If we're in a void that affects local measurements, the baryon acoustic oscillation patterns should show systematic variations that match the void predictions. Early results from these studies have been mixed. Some datasets seem to support the void hypothesis, while others show no clear signal. The challenge is that the effects are subtle and require extremely precise measurements across huge volumes of space. Another powerful test comes from measuring the peculiar velocities of galaxy clusters. Remember, peculiar velocity is the motion of an object due to gravity rather than cosmic expansion. If the void is real and has the properties we think it does, it should create a specific pattern of peculiar velocities. Galaxy clusters within the void should be moving outward faster than clusters outside it. Measuring these velocities is technically difficult. You need to know both the distance to each cluster and its redshift, then carefully separate the expansion component from the peculiar velocity component. But when done correctly, this method provides an independent check on the void hypothesis. Several research groups are working on mapping these velocity fields, and the results so far generally support the existence of large-scale outflows consistent with a void. A third approach involves looking at the cosmic microwave background in more detail. The void should leave an imprint on the microwave background through something called the integrated Sachs-Wolf effect. When photons from the cosmic microwave background travel through regions of changing gravitational potential, like an expanding void, they gain or lose energy in predictable ways. This creates temperature variations in the microwave background that correlate with the locations of voids and clusters. By comparing detailed maps of the cosmic microwave background with maps of large-scale structure, scientists can test whether the observed temperature patterns match what we'd expect from voids like the KBC. Again, the data so far seem to support the void picture, but more precise measurements are needed to be certain. Perhaps the most direct test will come from simply mapping more of the universe. The farther out we look, the better we can determine whether the KBC void is a unique freak of nature or part of a larger pattern. If similar supervoids show up frequently in deep surveys, it would suggest that the universe is more lumpy than standard models predict, which would require revising those models but wouldn't make our location particularly special. If, on the other hand, we map billions of light years in every direction, and find that supervoids like the KBC are genuinely rare, we'll have to seriously consider that we occupy an unusual location. That would raise uncomfortable questions about the cosmological principle and whether the universe is truly as uniform as we've assumed. Several next-generation surveys are specifically designed to address these questions. The Dark Energy Spectroscopic Instrument, or DESI, is measuring redshifts for tens of millions of galaxies across a huge volume of space. The Vera Rubin Observatory, formerly known as LSST, will provide deep imaging of billions of galaxies and map the large-scale structure in unprecedented detail. The European Space Agency's Euclid mission is measuring both the shapes and redshifts of galaxies to trace dark matter and dark energy across cosmic time. Together, these surveys will give us a much clearer picture of how common large voids are and whether the KBC void is truly exceptional. The stakes are high. If the void hypothesis is correct and our measurements have been biased by our location, it resolves the Hubble tension without requiring exotic new physics. That would be a relief in some ways, but it also means we've been systematically misunderstanding the universe for decades. Every measurement we've made of the expansion rate, dark energy, and the age of the universe would need to be reconsidered in light of our local environment. If the void hypothesis is wrong, we're back to square one on the Hubble tension. We'd need to find another explanation for why two precise, independent measurements of the expansion rate disagree so dramatically. That might mean new physics, modifications to gravity, evolving dark energy, or something we haven't even imagined yet. It might also mean there are systematic errors in one or both measurement methods that we haven't identified despite decades of scrutiny. Either way, the resolution will reshape our understanding of cosmology. The void hypothesis, whether right or wrong, has already forced us to think more carefully about how local structure affects our observations. Even if it turns out not to be the main explanation for the Hubble tension, it's shown us that we can't simply assume our neighborhood is typical. This lesson extends beyond the specific question of the void. It applies to any measurement we make of the universe. We have to account for our environment, our motion, our position in cosmic structure. We have to recognize that we're not observing from some privileged, neutral vantage point. We're embedded in the universe we're trying to study, and that embeddedness affects what we see. In a way, this brings us full circle to the Copernican revolution. Copernicus taught us that Earth isn't at the center of the solar system. Later, astronomers showed that the solar system isn't at the center of the galaxy, and the galaxy isn't at the center of anything. The cosmological principle took this to its logical conclusion. There is no center, and every location is equivalent. But now we're learning that while every location might be equivalent in principle, not every location is equivalent in practice. Some places are in voids, some are in clusters, some are in filaments. Where you are affects what you measure. This doesn't violate the cosmological principle in a strict sense. The universe is still the same on average when you zoom out far enough. But it adds an important caveat: local matters. This realization has implications beyond cosmology. In physics, we often search for universal laws that apply everywhere. But those laws play out in specific environments, and the environment affects the outcomes. A rock falling on Earth behaves differently than a rock falling on the Moon, not because gravity works differently, but because the environment is different. Similarly, the universe's expansion looks different from inside a void than from inside a cluster, not because the expansion itself is different, but because the local gravitational environment is different. Understanding this distinction is crucial for interpreting observations correctly. Let me give you another way to think about this. Imagine you're trying to measure the average temperature of the Earth. If you happen to live at the equator, your local measurements will show higher temperatures than the global average. If you live at the poles, your measurements will show lower temperatures. You're not wrong. You're accurately measuring your environment, but you can't assume your local measurement represents the whole planet. The same principle applies to cosmology. We're measuring the universe from Earth, which sits in a specific environment, the KBC void. Our measurements are accurate for this environment, but we have to be careful about extrapolating them to the universe as a whole. The challenge is figuring out exactly how much our local environment is affecting what we see. This is where the various tests I mentioned come in. By measuring baryon acoustic oscillations, peculiar velocities, the cosmic microwave background, and the large-scale distribution of galaxies, we can piece together a more complete picture. We can start to separate the universal properties of the cosmos from the local quirks of our neighborhood. The process is slow and painstaking, but it's how science works. We make observations, build models, test predictions, refine our understanding. Sometimes we discover that things we thought were universal are actually local. Sometimes we discover that things we thought were local are actually universal. The key is to remain open to both possibilities and let the data guide us. Right now, the data suggests the KBC void is real and does affect our measurements to some degree, but the magnitude of the effect and whether it fully explains the Hubble tension are still open questions. Over the next 5 to 10 years, as more data comes in from the surveys I mentioned, we should have much clearer answers. In the meantime, cosmologists continue to grapple with the implications. Some are excited by the prospect that a relatively simple explanation, we're in a void, might resolve a major crisis in the field. Others are skeptical that a void alone can produce a large enough effect. Still others worry that even if the void is real, it opens a Pandora's box of questions about the cosmological principle and our place in the cosmos. There's also a practical dimension to this debate. If we're going to spend billions of dollars on new telescopes and surveys to study dark energy and the expansion of the universe, we need to know whether our current measurements are reliable. If they're biased by the void, we need to account for that in planning future observations. If they're not biased, we need to understand what else might be causing the Hubble tension. These aren't just academic questions. They affect research priorities, funding decisions, and the direction of the field for decades to come. Getting the answer right matters, not just for our understanding of the universe, but for the practical business of doing cosmology. Beyond the science, there's something deeply fascinating about the idea that we live in a cosmic desert. It's humbling to realize that our galaxy, our supercluster, our entire local neighborhood exists in a region where matter is scarce. We're isolated on scales almost too large to comprehend. The nearest major concentration of galaxies is hundreds of millions of light years away. In some sense, we're cosmically alone. The universe is a vast, mostly empty place, and we happen to be in one of the emptiest parts. That doesn't make us special. Voids occupy most of the universe's volume, so most of space is in voids. But it does change your perspective to realize just how empty the cosmos really is. It also makes you appreciate the structure that does exist. The cosmic web, with its filaments and clusters, represents the triumph of gravity over expansion. These are the places where matter won the battle against cosmic dilution, where galaxies could form and stars could shine. The voids are the places where gravity lost, where matter is so sparse that structure couldn't take hold. We're fortunate, in a way, to live near the boundary between these two regimes. We're in a void, but not in the deepest part of it. We're close enough to the denser regions that galaxies still exist around us. We can see the cosmic web from our position, even as we participate in the void's dynamics. That gives us a unique perspective on how the universe is structured. If we lived in the very center of the void, the night sky would look dramatically different. There would be far fewer galaxies visible, and those that remained would be small and faint. The universe would seem emptier, lonelier. If we lived in a dense cluster, on the other hand, the sky would be ablaze with galaxies, and the dynamics would be dominated by cluster interactions rather than void expansion. Our actual position gives us a view that's somewhere in between. We see enough structure to understand how the universe is organized, but we're also subject to the void's influence on our measurements. It's a peculiar place to be, but perhaps that peculiarity is what makes it interesting. We're positioned to learn about both the full cosmos and the empty regions, to study both the presence and absence of matter. That perspective becomes even more interesting when you consider the history of astronomy. For most of human history, we thought we were at the center of everything. The Earth was the center of the universe, with everything else revolving around us. Copernicus shattered that illusion, showing that Earth orbits the Sun. Later, astronomers pushed the revolution further, showing that the Sun is just one star among hundreds of billions in the Milky Way, and the Milky Way is just one galaxy among hundreds of billions in the observable universe. Each discovery pushed us further from the center, made us less special, more ordinary. This progression is sometimes called the Copernican principle, the idea that we don't occupy a privileged position. It became a guiding philosophy in cosmology. When building models of the universe, cosmologists assumed that Earth's location is typical, that what we observe from here should be representative of what anyone anywhere would observe. The KBC void challenges that assumption in a subtle way. We're still not at the center of anything. Voids don't have centers in any meaningful sense. And even if they did, we're not quite at the center of this one. But we are in an unusual environment, one that affects our observations in measurable ways. That doesn't make us special in a cosmic sense, but it does mean we have to account for our environment when interpreting data. Some philosophers of science find this fascinating. It raises questions about how we can ever know whether our observations are universal or parochial. If we're always observing from some specific location, and that location always has some effect on what we see, how can we ever be sure we understand the universe as it truly is? The answer is that we can never be completely sure. We can only build models, test them against observations, and refine them as we gather more data. This is actually how all science works. We don't have access to absolute truth. We have observations, experiments, and models that explain those observations. The models are always approximations, always subject to revision as we learn more. What makes science powerful is not that it gives us certainty, but that it gives us a method for progressively improving our understanding. The void hypothesis is a perfect example of this process in action. For decades, we built cosmological models, assuming our location was typical. Those models worked well for many observations, but struggled to explain the Hubble tension. The void hypothesis suggests that one of our assumptions, that our location is typical, might need to be relaxed. If that's correct, it improves our models and resolves the tension. If it's not correct, we'll learn that from future observations and adjust accordingly. This kind of iterative refinement is the essence of scientific progress. It's messier than the clean, linear narrative we often present in textbooks, but it's how real science gets done. We propose hypotheses, test them, revise them, test again. Sometimes we discover that our instruments were biased. Sometimes we discover that our assumptions were wrong. Sometimes we discover that nature is more complex than we thought. The void hypothesis, if confirmed, would be an example of discovering that our assumptions were wrong. We assumed our local measurements of the expansion rate reflected universal properties. If the void affects those measurements significantly, that assumption was incorrect. We weren't measuring the universe as a whole. We were measuring our local environment. That's not a failure of science. It's science working as intended, correcting its own errors through better observations and deeper analysis. It's worth noting that even if the void fully explains the Hubble tension, cosmology would still face major unsolved mysteries. We still don't know what dark matter is. We still don't know what dark energy is. We still don't fully understand how galaxies form and evolve. We still don't know whether there are other universes beyond our own. The void hypothesis, at best, resolves one puzzle. It doesn't answer all the questions, but resolving even one major puzzle would be significant. The Hubble tension has been a source of frustration and excitement in cosmology for over a decade. Frustration because it suggests something is wrong with our understanding. Excitement because resolving it might lead to new discoveries. If the void is the answer, that would be satisfying in some ways. It's an explanation that doesn't require exotic new physics, but also disappointing in others, because it means the tension wasn't pointing toward revolutionary new physics after all. On the other hand, if the void isn't the answer, and we need to invoke new physics to explain the tension, that could be even more exciting. It might mean dark energy evolves over time, or gravity works differently on cosmic scales, or there are particles we haven't detected yet. Any of those discoveries would be profound and would reshape fundamental physics, not just cosmology. So we're at a crossroads. The data we gather over the next decade will determine which path we take. Either way, we'll learn something important about the universe. That's what makes this such an exciting time in cosmology. We're on the verge of major discoveries, and we don't yet know which direction they'll take us. Let me shift gears and talk about what life would be like in different parts of the universe. If you were in the densest part of a galaxy cluster, the night sky would be spectacular. Galaxies would be everywhere, many of them close enough to show structure with the naked eye. You'd see spiral arms, glowing nebulae, the bulges of elliptical galaxies. The sky would never be truly dark, but you'd also be in danger. Galaxy clusters are violent places. Galaxies collide and merge regularly. Stars are stripped from their home galaxies by tidal forces. Supermassive black holes in galactic centers occasionally flare up, blasting radiation across millions of light years. If you were on a planet in a cluster, your sky might occasionally light up with the flash of a quasar or the glow of a galaxy merger. Beautiful, but perhaps not the most stable environment for life to evolve. In a void, the opposite would be true. The sky would be mostly empty. If you were on a planet in a void galaxy, you might see a handful of other galaxies, all of them small and faint and far away. The rest of the sky would be black, filled only with the faint glow of the cosmic microwave background. It would be profoundly lonely, but it would also be safe. Void galaxies rarely interact with neighbors. They evolve in isolation, slowly and peacefully. There are no galaxy collisions, no quasar flares, no tidal disruptions. If you're looking for a stable environment for life to evolve over billions of years, a void galaxy might actually be ideal, quiet, uneventful, but safe. Our position in the KBC void, near the edge rather than in the center, gives us a bit of both worlds. We have enough neighbors to make the sky interesting. Andromeda is visible with the naked eye, and there are other galaxies scattered across the sky. But we're not in a crowded cluster where interactions are constant. We're in a relatively calm region where galaxies can evolve without too much interference. This might not be a coincidence. Some researchers have speculated that complex life might preferentially evolve in environments like ours, not too crowded, not too empty. In the densest clusters, radiation levels might be too high, or galaxy interactions might disrupt planetary systems too frequently. In the emptiest voids, there might not be enough heavy elements to form rocky planets and organic molecules. The regions in between, like where we are, might be the Goldilocks zone for life. Not too hot, not too cold, just right. This is highly speculative, of course. We don't know enough about how life forms and evolves to say with confidence what conditions are necessary. But it's an interesting thought that our location might not be random, that there might be selection effects at play. If most intelligent observers find themselves in environments similar to ours, that would affect how we think about the cosmological principle. It would mean that while the universe as a whole might be uniform, the locations where observers exist might be clustered in certain types of environments. That wouldn't violate the principle. the universe would still be the same on average, but it would add nuance to how we apply it. This kind of reasoning is called anthropic reasoning, and it's controversial among physicists. Some think it's a legitimate way to incorporate observational selection effects into our models. Others think it's circular reasoning that doesn't really explain anything. The debate continues, and the void hypothesis is caught up in it. If we're in a void purely by chance, with no selection effects involved, then the statistical rarity of the KBC void is a serious problem. It suggests either we're incredibly lucky or our models are wrong about how rare such voids should be. But if there are anthropic selection effects, if observers tend to find themselves in environments like ours for physical reasons, then the rarity is less problematic. It's rare for a random location to be in such a void, but it's not rare for an observer to be in such a void if that's where observers tend to arise. Which interpretation is correct? We don't know yet, and to some extent it might not matter for the practical question of whether the void affects our measurements. Even if there are selection effects that make it unsurprising that we're in a void, the void still exists and still affects what we observe. The philosophical questions about why we're in a void are separate from the empirical questions about what the void does to our observations. That said, the philosophical questions are interesting in their own right. They touch on deep issues about the nature of scientific explanation, the role of chance in the universe, and what it means to be an observer in a cosmos that might or might not be designed for observers. These aren't questions science can fully answer, but science can inform them by telling us what the universe is actually like. And what the universe is actually like, as far as we can tell, is a vast, mostly empty expanse punctuated by occasional islands of structure. Voids dominate by volume, filaments and clusters by mass. The cosmic web stretches across billions of light years, shaped by gravity and dark energy into patterns that encode the history of the universe from its earliest moments to the present. We're part of that structure, embedded in it, shaped by it. The void we live in affects our motion, our observations, and possibly even our existence. Understanding that void is understanding our place in the cosmos. It's a piece of the larger puzzle of how the universe works, how it came to be this way, and where it's going. The future of the void is tied to the future of the universe as a whole. As dark energy continues to drive accelerated expansion, voids will grow larger and emptier. The filaments connecting them will stretch and thin. Galaxy clusters will become more isolated. Eventually, over timescales of hundreds of billions of years, the cosmic web will dissolve. The universe will become a vast expanse of darkness, with isolated clusters of galaxies separated by unimaginable distances. Within those clusters, stars will continue to form and die for a time. But as the gas supply runs out, and existing stars burn through their fuel, star formation will cease. The clusters will be left with only the remnants: white dwarfs, neutron stars, black holes. These will slowly evaporate or merge over timescales of trillions of years. Eventually, even the black holes will evaporate through Hawking radiation, leaving nothing but a thin soup of elementary particles expanding ever outward. This is the heat death of the universe, the eventual fate predicted by our current understanding of physics. The void we live in is a preview of that future. It's already a place where matter is scarce and structure is minimal. As the universe ages, more and more of it will come to resemble voids. The clusters and filaments are temporary concentrations that will eventually dissipate. The voids are forever. That's a bleak vision in some ways, but it's also strangely beautiful. The universe had a beginning, and it will have an end. In between, there's a brief period, brief on cosmic timescales, though it spans trillions of years by human reckoning, when structure exists, when stars shine, when life can arise and contemplate its origins. We're living in that brief window, and we're fortunate to be able to witness and study the cosmos while it's still interesting. The void also tells us something profound about scale. Human intuition evolved to deal with scales we can directly perceive: the size of our bodies, the distance we can walk in a day, objects we can hold in our hands. We have no natural intuition for scales millions or billions of times larger or smaller. That's why cosmic scales are so difficult to grasp emotionally, even when we understand them intellectually. A billion light years is a distance so vast that light, traveling at the fastest speed possible in our universe, takes a billion years to cross it. In that time, civilizations could rise and fall, species could evolve and go extinct, stars could be born and die. The void we live in is 2 billion light years across. Every thought you've ever had, every human who's ever lived, every monument we've built, every war we've fought, all of human history is a fleeting instant compared to the time it takes light to cross this void. And yet, in another sense, the void is small. The observable universe extends about 93 billion light-years in all directions. The KBC void is only about 2% of that diameter. On the largest scales we can observe, the void is just one feature among many. It's simultaneously unimaginably vast and cosmically modest. This dual nature, vast by human standards, modest by cosmic standards, applies to everything in astronomy. The sun seems huge to us, but it's a medium-sized star. star, unremarkable among the hundreds of billions in our galaxy. The Milky Way seems enormous, but it's a medium-sized galaxy, unremarkable among the hundreds of billions in the observable universe. Even the observable universe itself might be just a tiny fraction of the total universe, which could extend vastly beyond what we can see. Each time we zoom out, what seemed important at the previous scale becomes ordinary. Earth seemed like the whole universe until we discovered other planets. The solar system seemed vast until we discovered other stars. The galaxy seemed immense until we discovered other galaxies. The observable universe seems infinite until cosmologists speculate about inflation and multiverses. There's always another scale beyond the one we can currently perceive. The void fits into this hierarchy. It seemed shocking when first discovered. How could we be in such an unusual place? But as we map more of the universe, we're finding that large voids aren't as rare as we initially thought. They're uncommon, yes, but not unique. The universe is full of structure on all scales, and voids are part of that structure. The KBC void is notable for being large and for being our local neighborhood, but it's not a cosmic anomaly. This is actually reassuring in a way. It means the cosmological principle might be safe after all. The universe really is roughly uniform when you zoom out far enough. Yes, there's structure, filaments, clusters, voids, but that structure is the natural consequence of gravitational instability acting on random initial conditions. It's what you'd expect from the laws of physics, not something that requires special explanation. Of course, we still need to verify this with observations. We need to map more of the universe, find more voids, measure their properties, and confirm that they match theoretical predictions. That's what the next generation of surveys will do. They'll either confirm that large voids are a natural part of cosmic structure, or they'll reveal something unexpected that requires new physics. Let me talk a bit about the technology that makes all this possible. When the first astronomers mapped the cosmic web in the 1970s and 80s, they had to measure galaxy redshifts one at a time. Each measurement required hours of telescope time. Building a three-dimensional map of even a small region of space took years of work. Today we have instruments that can measure hundreds or thousands of redshifts simultaneously. Fiber optic spectrographs can observe multiple galaxies at once, dramatically speeding up the process. Digital detectors are far more sensitive than photographic plates, allowing us to see fainter and more distant objects. Automated data processing can handle the flood of information these instruments produce. The dark energy spectroscopic instrument is a perfect example. It has 5,000 fiber optic cables, each positioned by a robot to point at a specific galaxy. In a single observation, it can measure the spectra of 5,000 galaxies simultaneously. Over the course of its 5-year survey, it will measure spectra for more than 40 million galaxies and quasars. That's an unprecedented map of cosmic structure. Similarly, the Vera Rubin Observatory will use a massive camera, the largest ever built for astronomy, to photograph the entire visible sky every few nights. Over 10 years, it will detect billions of galaxies and track how their positions change over time. This data will reveal the cosmic web in exquisite detail and allow us to study voids, filaments, and clusters with statistical precision. These surveys are expensive, hundreds of millions of dollars each, but they represent a revolution in our ability to map the universe. Just as Google Earth transformed our ability to explore our own planet, these surveys are transforming our ability to explore the cosmos. We're moving from a regime where we had scattered observations of small regions to one where we have comprehensive maps of vast volumes. This technological progress enables scientific progress. Questions that were purely theoretical a generation ago, like whether the KBC void significantly affects local measurements, are now becoming empirically testable. We'll have the data to answer them definitively within the next decade. That's an exciting prospect. Of course, technology alone isn't enough. We also need the theoretical framework to interpret the data. That's where the mathematical models and computer simulations come in. Cosmologists use supercomputers to simulate the evolution of the universe from the Big Bang to the present. These simulations start with the tiny density fluctuations encoded in the cosmic microwave background and evolve them forward in time using the laws of physics. The resulting simulated universes can then be compared to observations. Do the simulations produce structures that look like what we see? Are voids as large and as common in simulations as they are in reality? If the simulations match observations, that validates our understanding of the physics. If they don't match, it suggests something is missing from our models. Current simulations generally do a good job of reproducing the cosmic web. They produce filaments, clusters, and voids that resemble what we observe, but they struggle to reproduce voids as large and as deep as the KBC void. This could mean our models are missing something, or it could mean the KBC void is simply a rare statistical fluctuation that happens to exist but isn't common in most simulations. To distinguish between these possibilities, we need more data. If we find many more large voids, It suggests the models need adjustment. If large voids remain rare, it supports the idea that the KBC void is just a lucky or unlucky draw, depending on your perspective. Either way, the combination of observations and simulations will give us the answer. There's also the question of what's happening on even larger scales. The observable universe extends much farther than we've mapped in detail. Could there be even larger structures out there, supervoids dwarfing the KBC, or super-superclusters that make Laniakea look small? Or does structure eventually smooth out, confirming that the universe is uniform on sufficiently large scales? Recent observations suggest that structure does smooth out beyond a few hundred million light-years. When you look at scales larger than that, the universe appears increasingly uniform. The fluctuations in density get smaller and smaller as you zoom out. This supports the cosmological principle and suggests that the universe really is homogeneous on the larger scales, but there have been hints, controversial and not yet confirmed, of structure on even larger scales. Some studies have claimed to detect alignment of galaxy spins or patterns in the cosmic microwave background that extend across billions of light-years. If real, these would be problematic for the standard cosmological model, but most cosmologists are skeptical. The signals are weak, and there are alternative explanations that don't require large-scale structure. This is how science works. Someone claims to detect something unexpected. Others try to verify it with independent data. If it holds up, it becomes accepted. If it doesn't, it's discarded. Right now, the balance of evidence supports homogeneity on large scales, but the door is open to surprises. Let's consider what it would mean if the universe turns out not to be homogeneous on the largest scales. That would be a profound discovery, potentially more significant than the void itself. It would suggest that the cosmological principle is wrong, that the universe has structure all the way up, no matter how far you zoom out. That would require a complete rethinking of our cosmological models. Some alternative cosmologies already explore this possibility. Fractal universe models, for instance, propose that structure exists at all scales, with no level at which homogeneity kicks in. These models are mathematically interesting but face challenges in matching observations, particularly the cosmic microwave background, which looks very uniform. Another possibility is that our observable universe is just one patch of a much larger multiverse. Different patches could have different properties, different densities, different expansion rates, even different physical laws. If that's the case, asking whether the universe is homogeneous might not even make sense. It would depend on which patch you're asking about. These are speculative ideas, far beyond what current data can confirm or rule out, but they illustrate how discovering something like the KBC void can open up new avenues of thought. Even if the void turns out to be entirely consistent with standard cosmology, the process of investigating it has forced us to think more carefully about assumptions we'd taken for granted. That's valuable in itself. Science progresses not just by discovering new facts, but by questioning old assumptions. Sometimes those assumptions turn out to be correct, and we understand them better after testing them. Sometimes they turn out to be wrong, and we make breakthroughs by discarding them. Either way, the process of questioning and testing is essential. The KBC void has sparked exactly this kind of questioning. Are we in a typical location? Does our local environment bias our measurements? Is the universe as uniform as we thought? These questions were always implicit in cosmology, but the void has made them explicit and urgent. Regardless of how the debate resolves, we'll come out with a deeper understanding of the cosmos and our place in it. There's also a historical dimension to this story. The discovery of the void in 2013 came at a time when cosmology seemed to be entering a period of precision measurement. We had the lambda cold dark matter model, which worked well for most observations. We had measurements of the cosmic microwave background from satellites like Planck. We had surveys mapping the large-scale structure. Everything seemed to be falling into place. Then the Hubble tension emerged. Different measurements of the expansion rate disagreed, and the disagreement was statistically significant. This was troubling. Either our measurements had unknown systematic errors, or something was wrong with the model. The void hypothesis offered a potential resolution, a way to reconcile the measurements without abandoning the model. Whether the void hypothesis is correct or not, the Hubble tension has reminded cosmologists that even in an era of precision measurement, surprises can emerge. The universe is complex, and our understanding is always incomplete. That's humbling, but it's also exciting. It means there's still room for discovery, still puzzles to solve, still opportunities to learn something new. This brings us to a broader point about scientific progress. It's not linear. It doesn't proceed smoothly from ignorance to knowledge. Instead, it's a messy, iterative process. We build models, test them, find discrepancies, revise the models, test again. Sometimes we go down blind alleys, sometimes we make leaps forward, but we're always building on what came before, refining our understanding step by step. The void story is still unfolding. We don't yet know the ending. Will the void fully explain the Hubble tension? Will it require modifications to our models? Will it turn out to be a red herring, with the real answer lying elsewhere? We won't know until we have more data, and that data is coming. The surveys are running, the telescopes are observing, the data is being analyzed. In a few years, we'll have much clearer answers. In the meantime, what can we take away from the void story so far? First, it reminds us that our local environment matters. We can't assume that what we measure from Earth automatically applies to the entire universe. We have to account for where we are, what structures surround us, and how those structures affect our observations. This lesson applies not just to cosmology, but to any science that deals with systems larger than we can directly sample. Second, it shows the power of combining different types of observations. The void hypothesis emerged from looking at galaxy surveys, but it's being tested with measurements of peculiar velocities, the cosmic microwave background, baryon acoustic oscillations, and more. Each method provides independent information, and when multiple methods agree, that strengthens our confidence. When they disagree, it tells us something interesting is happening. Third, it illustrates how statistical thinking is crucial in cosmology. We can't simply dismiss the KBC void as impossible because it's rare. Rare things happen. But we do need to ask how rare it is, whether our models predict the right level of rarity, and whether there are selection effects we're not accounting for. These are subtle questions that require careful statistical analysis. Fourth, it demonstrates the importance of humility in science. Even when we think we have something figured out, like the expansion rate of the universe, nature can surprise us. Being willing to revisit assumptions, consider alternative explanations, and admit uncertainty is what allows science to self-correct and improve over time. Let me address one common misconception about the void. Some people hear that we're in a cosmic hole and imagine that the void is somehow pulling us in, like a black hole. That's not what's happening. The void isn't a gravitational well that traps things. In fact, it's the opposite. The void is a region of below average density, which means there's less gravity inside it than outside. The gravitational gradient points outward, not inward. We're not falling into the void. We're being pushed out of it by the gravitational attraction of the denser regions beyond its edges. But because those denser regions are so far away, hundreds of millions of light years, the effect is relatively gentle. We're moving at 600,000 miles per hour, which sounds fast, but on cosmic scales it's almost leisurely. It will take hundreds of millions of years for us to reach the edge of the void at this rate. And by the time we get there, the void will have expanded due to the accelerating expansion of the universe. So in a sense, we're chasing a receding target. We'll never actually escape the void in any meaningful sense. We're part of it, embedded in its dynamics, for the duration of the universe's future. This raises an interesting question about the long-term fate of structure in the universe. Right now, galaxy clusters are bound together by gravity. They're not expanding with the rest of the universe because the gravity within them is strong enough to overcome the expansion. But as dark energy continues to drive accelerated expansion, will even these bound structures eventually be torn apart? The answer depends on the nature of dark energy. If dark energy is a cosmological constant, a fixed property of space, then bound structures will remain bound forever. The expansion affects only the space between structures, not the structures themselves. Galaxy clusters will stay intact even as the voids around them expand. But if dark energy grows stronger over time, as some models propose, it could eventually overcome even the strongest gravitational binding. In the most extreme scenario, called the Big Rip, dark energy would grow so strong that it would tear apart galaxies, solar systems, planets, and eventually even atoms. This would happen in the far future, tens of billions of years from now at the earliest, but it would be a dramatic end to all structure. Current observations suggest dark energy is consistent with being a cosmological constant, which means the Big Rip probably won't happen, but we can't rule it out with certainty. Measuring whether dark energy evolves over time is one of the major goals of current and future cosmological surveys. The answer will tell us not just about the expansion rate, but about the ultimate fate of everything in the universe. The void plays into this question because different regions of the universe might be affected differently by dark energy evolution. If dark energy is truly constant, it affects voids and clusters the same way. But if it evolves, the effects might be more pronounced in underdense regions like voids. Studying how voids evolve over time could therefore give us clues about the nature of dark energy. This is why cosmologists care so much about understanding voids. They're not just empty regions to be ignored. They're laboratories for studying dark energy, gravity, and the evolution of cosmic structure. The fact that we live in one gives us a unique perspective on these phenomena. Let me return to the question of whether we're special. I've discussed how the void challenges the assumption that our location is typical, but there's another sense in which we might or might not be special: the timing of our observations. We happen to be making these measurements now at a specific moment in cosmic history. Is this timing random, or is there something special about this era? Consider that we're living roughly 14 billion years after the Big Bang. Stars have been shining for about 13 billion years. Complex elements have had time to form and accumulate. Planets have formed. Life has emerged. Intelligence has evolved. We're in what you might call the middle age of the universe, not too early, when conditions were too hostile for life, and not too late, when stars will have burned out and the universe will be dark. Is it a coincidence that we're making precise measurements of cosmology during this era? Or is there an anthropic explanation that observers can only exist during this era, so of course we find ourselves making observations now? This is another example of the anthropic reasoning I mentioned earlier, and it's equally controversial. Some cosmologists think anthropic reasoning is vacuous, others think it's a legitimate way to incorporate selection effects. The debate probably won't be resolved anytime soon, but it's worth noting that our ability to study the universe depends on our existence, and our existence depends on the universe having certain properties at certain times. That doesn't mean the universe was designed for us, but it does mean we should be cautious about assuming our observations are universal. The void fits into this picture in an interesting way. If observers tend to emerge in intermediate density regions like the outskirts of voids, then many observers would be making cosmological measurements from similar environments. That would mean the typical observational perspective is actually biased in a systematic way. This doesn't help any individual observer figure out the true cosmic parameters, but it does suggest that many observers would face the same challenges we do. Another aspect of the void that deserves attention is its role in the broader structure of the universe. The cosmic web isn't just a random collection of voids, filaments, and clusters. It's a hierarchical structure with patterns on multiple scales. Small voids connect to form larger voids. Filaments branch and merge. Clusters sit at the nodes where filaments intersect. This hierarchical structure is a natural consequence of gravitational collapse. Small overdensities collapse first, forming the seeds of galaxies and small clusters. These merge over time to form larger structures. Meanwhile, the regions between the overdensities expand into voids. The process happens on all scales, creating the fractal-like patterns we observe. The KBC void is part of this hierarchy. It's connected to smaller voids like the local void, and it's probably part of a larger pattern of structure that extends beyond what we've mapped so far. Understanding how voids fit into this hierarchy helps us understand how structure forms and evolves over cosmic time. One prediction of the hierarchical model is that voids should have distinct properties depending on their size and age. Young voids, recently emptied by structure formation, might have different density profiles than old voids that have been expanding for billions of years. Large voids might form through different processes than small ones. Testing these predictions requires careful observations of many voids at different distances and redshifts. The upcoming surveys will provide exactly this data. By measuring the properties of hundreds or thousands of voids across a large volume of space, we'll be able to test whether they match theoretical predictions. This will either validate our understanding of structure formation or reveal discrepancies that point toward new physics. There's also the question of what happens inside voids over time. As they expand and become emptier, do galaxies within them evolve differently than galaxies in denser regions? The answer appears to be yes. Void galaxies tend to be smaller, bluer, and more gas-rich than galaxies in clusters. They form stars more slowly and have had fewer interactions with neighbors. This makes sense given their environment. With no nearby galaxies to collide with or strip gas from them, void galaxies can hold onto their gas and form stars at a leisurely pace. They're like isolated homesteads on the cosmic frontier, far from the bustle of the galaxy clusters. This isolation means they preserve a record of conditions from earlier cosmic epochs. They haven't been disrupted or transformed by interactions. Studying void galaxies can therefore tell us about galaxy evolution in relatively pristine environments. By comparing them to cluster galaxies, which have experienced lots of interactions, we can isolate the effects of environment on galaxy properties. This is valuable for understanding the full range of ways galaxies can form and evolve. Our own Milky Way, being in the KBC void but not deeply inside it, occupies a middle ground. We're not in the densest clusters where interactions are frequent, but we're not in the deepest voids where galaxies are truly isolated. We have neighbors, Andromeda, the Magellanic Clouds, other members of the local group, but we're not constantly colliding with them. This might be an ideal environment for life. Frequent galaxy collisions could disrupt planetary systems or flood regions with radiation from quasars and supernovae. Too much isolation might mean fewer heavy elements to form planets with. Our intermediate environment gives us stability without complete isolation. Again, this might not be a coincidence if there are anthropic selection effects at play. Let me talk about one more aspect of the void, its implications for the search for extraterrestrial extraterrestrial intelligence. If we're in an unusual environment, does that affect the likelihood that other intelligent civilizations exist nearby? And if they exist, would they face the same challenges we do in understanding cosmology? On one hand, if void environments are favorable for life, there might be many civilizations in the KBC void. We'd all be dealing with similar observational challenges, all trying to figure out whether we're in typical locations. We might all arrive at similar conclusions about the expansion rate, not realizing we're all being biased by the same local structure. On the other hand, the void is less dense than average, which might mean fewer habitable planets overall. The nearest intelligent civilizations could be farther away than they would be if we were in a denser region. That could make contact more difficult, not just because of distance, but because any signals would have to travel through vast, empty spaces where there are few stars to pass by. This is all speculative, of course. We have no evidence of extraterrestrial intelligence, let alone any understanding of where such civilizations might be located, but it's an interesting thought experiment. If we ever do make contact, comparing notes about what different civilizations observe from their locations could be incredibly valuable for understanding the universe. Imagine a civilization in a dense cluster observing the universe. They'd see galaxies everywhere, measure a lower local expansion rate due to the cluster's gravity, and probably arrive at different cosmological parameters than we do. A civilization deep in a void would see even fewer galaxies than we do, and might measure an even higher apparent expansion rate. Only by comparing observations from multiple locations could any of us determine the true cosmic parameters. This is actually what we're trying to do now, in a sense. We can't physically travel to different locations in the universe, but we can observe different regions and compare what we see. By measuring the expansion rate at different distances and in different directions, we can start to separate local effects from universal properties. It's like triangulating from multiple vantage points to determine the true shape of something. The void hypothesis is essentially an attempt at this triangulation. It says we're measuring from here, which is inside a void. If we account for the void's effects, the measurements should agree with measurements from elsewhere. The next few years will test whether this triangulation works, whether we can successfully separate our local environment from the cosmic background. Whether it works or not, the exercise is valuable. It's teaching us to think more carefully about observational biases, local environments, and the assumptions we make when interpreting data. These lessons will apply to future observations, even if the specific question of the KBC void gets resolved. As we approach the end of this exploration, let me bring things back to the human level. What does it mean for you, personally, to live in a cosmic void? In practical terms, nothing at all. Your daily life is unaffected. The void doesn't change how gravity works on Earth, how the sun shines, or how stars appear in the night sky. The effects are too subtle and too large-scale to matter for anything except cosmological measurements. But on a philosophical level, it changes your cosmic address. You're not just on Earth, in the solar system, in the Milky Way, in the local group, in the Laniakea supercluster. You're also in the KBC void, a region of below-average density spanning 2 billion light-years. That's part of your location in the universe. It's part of what makes your vantage point unique. Think about what that means for your perspective on existence. Every human who has ever lived has gazed up at the night sky from this location. Every scientific observation ever made, every philosophical reflection on our place in the cosmos has been shaped by this environment. We've never known anything else. The void is our cosmic home, and it colors everything we see. If humanity ever becomes a spacefaring civilization and spreads beyond our galaxy, future generations will have different perspectives. Some might settle in galaxy clusters, where the sky is filled with neighboring galaxies and interactions are frequent. Others might venture into deeper voids, where the isolation is nearly complete. Each group would see the universe differently, measure different things, and probably develop different intuitions about how the cosmos works. But for now, we're all here, in this void, looking out at the universe together. That shared perspective is part of what unites humanity. We're all trying to make sense of the same view, the same data, the same cosmic environment. The questions we're asking about the void are questions about our place in the universe, and therefore questions about ourselves. One thing the void teaches us is the value of perspective. From inside the void, the universe looks a certain way. From outside, it would look different. Neither perspective is wrong, but neither is complete. To understand the whole picture, you need to combine multiple perspectives, correct for local biases, and try to see beyond your immediate environment. This lesson applies to much more than cosmology. In daily life, we all see the world from our particular perspective, shaped by our experiences, culture, and environment. It's easy to assume our perspective is universal, that everyone sees things the way we do, but they don't. Everyone has their own vantage point, their own local environment affecting their observations. Science teaches us to recognize this and account for it. We do experiments in different locations, under different conditions, with different instruments. We compare results, look for systematic biases, and try to separate universal truths from local artifacts. The void hypothesis is an example of this process at the largest possible scale, recognizing that our cosmic environment might be biasing our observations and trying to correct for it. The process of doing science is, in many ways, the process of overcoming our local perspective to glimpse universal truths. We can never completely escape our perspective. We're always observing from somewhere, at some time, with some set of instruments and assumptions. But we can become aware of how our perspective shapes what we see, and we can develop methods to account for it. The void reminds us that this applies even at cosmic scales. We can't assume that what we measure from Earth automatically applies everywhere. We have to think about where we are, how we're moving, what structures surround us. We have to be humble about the limitations of our perspective, while also being confident in our ability to gradually overcome those limitations through careful observation and analysis. Let me address one final question. Should we be concerned about the void? Is there any danger associated with living in such a region? The answer is no. The void affects cosmological measurements, but it doesn't pose any threat to Earth, the solar system, or the Milky Way. We're not going to be sucked into some cosmic drain or crushed by the void's expansion. The dynamics of the void play out over hundreds of millions of years. Even though we're moving at 600,000 miles per hour away from the local void, that motion is imperceptible on human timescales. In all of recorded human history, we've moved less than a millionth of the distance across the void. The sun will burn out, the Earth will be uninhabitable, and humanity will either be long extinct or have spread to the stars long before our motion through the void becomes significant. The expansion of the void, driven by dark energy, is similarly slow on human scales. Yes, the void is growing, and eventually it will consume more and more of the universe. But this happens over timescales of billions of years. The near-term fate of humanity has nothing to do with the void, and everything to do with how we manage our planet and our civilization. So the void is not a danger. It's simply a feature of our cosmic environment, one that we're only now beginning to understand. Discovering it doesn't change our fate, it changes our knowledge. And knowledge, even when it reveals uncomfortable truths about our location or our measurements, is always valuable. One of the beautiful things about the void story is how it demonstrates the power of human curiosity and ingenuity. 3 astronomers noticed something odd in galaxy counts. They investigated, checked their work, and published their findings. Other scientists examined the data, proposed explanations, and began testing predictions. Slowly, painstakingly, the community has built up an understanding of what the void is, how it formed, and what it means for our observations. This is science at its best, a collective effort to understand nature driven by curiosity and tested against observation. No single person figured out the void. It emerged from the work of many researchers, each contributing their piece to the larger puzzle. Some focused on observations, others on theory, still others on simulations. Together, they've advanced our understanding dramatically in just over a decade. The story is ongoing. The questions aren't all answered yet, but the progress has been real and significant. We know far more about the void now than we did in 2013. And in another decade, assuming the surveys proceed as planned, we'll know even more. Perhaps we'll have definitive answers to whether the void fully explains the Hubble tension, whether similar voids are common, and what it all means for the cosmological principle. Whatever we learn, the void has already left its mark on cosmology. It's forced us to think more carefully about our assumptions, our methods, and our interpretations. It's reminded us that the universe is vast and complex, full of structures on scales we're still learning to measure. It's shown us that even in an era of precision cosmology, there's room for surprise and discovery. These lessons will endure regardless of how the specific questions about the void are resolved. Future cosmologists will study even larger structures, even fainter galaxies, even more subtle effects. They'll face new challenges and new puzzles. But the fundamental approach, careful observation, rigorous analysis, willingness to question assumptions will remain the same. Let me also acknowledge the limitations of what we know. Despite all the progress, there's still enormous uncertainty about many aspects of the void. We don't know exactly how deep it is, exactly where its boundaries are, or exactly how it formed. We don't know for sure how much it affects our measurements of the expansion rate. We don't know whether it's a rare statistical fluke or part of a larger pattern we haven't recognized yet. These uncertainties are frustrating, but they're also what makes the science exciting. If we knew everything, there would be nothing left to discover. The fact that major questions remain open means there's still work to do, still observations to make, still theories to test. The next generation of astronomers and cosmologists will have the opportunity to answer questions we're only beginning to formulate. They'll have better instruments than we do now. The James Webb Space Telescope is already revolutionizing our view of the early universe. The next generation of ground-based telescopes, the Extremely Large Telescope, the 30-meter telescope, the Giant Magellan Telescope, will have unprecedented light-gathering power and resolution. Space-based space-based missions like Euclid and the Roman Space Telescope will map cosmic structure in extraordinary detail. These instruments will allow us to study voids at much greater distances and with much higher precision than is currently possible. We'll be able to trace how voids evolve over cosmic time, from the early universe when they were just forming to the present day when they dominate the volume of space. This evolutionary picture will test our theories of structure formation and potentially reveal new physics. There's also the possibility of entirely new types of observations. Gravitational wave detectors might eventually become sensitive enough to detect the gravitational waves from galaxy mergers or from turbulence in the cosmic web. Neutrino detectors could map the distribution of matter using neutrinos instead of light. Radio telescopes could detect the faint glow of neutral hydrogen in voids, tracing gas that's invisible to optical telescopes. Each new type of observation gives us a different window on the universe. Light shows us where stars and galaxies are. Gravitational waves show us where massive objects are accelerating. Neutrinos show us where nuclear reactions are happening. Radio waves show us where cold gas exists. By combining all these different windows, we build up a complete picture of cosmic structure. The void will be studied using all of these methods. Each will reveal different aspects of its nature. Together, they'll give us a comprehensive understanding of what voids are, how they work, and what they mean for the universe as a whole. This multifaceted approach is the future of astronomy and cosmology. As we push toward that future, it's worth appreciating how far we've already come. A century ago, we didn't even know galaxies were separate from the Milky Way. We thought the universe was static, unchanging, and probably eternal. In just 100 years, we've discovered that the universe is expanding, that it began in a Big Bang, that it's filled with dark matter and dark energy, and that it has a complex web-like structure on the largest scales. We've measured the age of the universe to within 1%. We've mapped the cosmic microwave background in exquisite detail. We've detected gravitational waves from colliding black holes. We've found thousands of planets around other stars. We've glimpsed galaxies as they appeared just a few 100 million years after the Big Bang. The progress has been breathtaking. The discovery of the KBC void is part of this larger story of discovery. It's another piece of the puzzle, another insight into how the universe is structured and how it works. It might seem like a small piece, just one void among many, but it's the void we live in, and understanding it helps us understand our place in the cosmos. That's ultimately what cosmology is about, understanding our place in the universe, not in an egocentric way, but in a humble, curious way. We want to know where we are, how we got here, what surrounds us, and where we're going. The void is part of that story. It's part of our cosmic home, our address in the universe, our vantage point on reality. Living in a void doesn't make us special or cursed. It simply makes us inhabitants of a particular type of environment, one that has certain properties and certain effects on what we observe. Understanding those properties and effects is part of understanding ourselves and our relationship to the larger cosmos. That's what makes the void worth studying, worth thinking about, worth the effort of decades of observations and analysis. So when you look up at the night sky, remember, you're looking out from inside a cosmic desert, a region where matter is scarce and space stretches thin. The stars you see are nearby neighbors in that desert. The distant galaxies are like oases on the horizon. Beyond them, hundreds of millions of light years away, lie the denser regions where galaxies cluster and the universe comes alive with structure and motion. You're on the edge of emptiness, gazing out at the wider cosmos, trying to make sense of it all from your particular vantage point. That's a profound thing to contemplate. It connects you to the larger structures in nature and to the deepest questions about existence. The void isn't just a feature of space, it's part of your story, part of humanity's story, part of the eternal human quest to understand the universe we inhabit. Part 10, Finale, 12,000 plus characters. We've covered an enormous amount of ground in this exploration, from the initial discovery of missing galaxies to the implications for the Hubble tension, from the physics of voids to the philosophical questions about our place in the universe. Now it's time to bring all these threads together and look toward the future. What happens next in the story of the cosmic void? The immediate future involves more observations and better data. The surveys I mentioned, DESI, Euclid, the Vera Rubin Observatory, are actively collecting information that will help resolve the outstanding questions. Within the next 3 to 5 years, we should have much clearer answers about the void's properties, its effects on measurements, and how common similar structures are in the wider universe. If these surveys confirm that the void fully explains the Hubble tension, that will be a major resolution to one of cosmology's biggest puzzles. It will mean our models are fundamentally correct, but we need to account more carefully for local environmental effects. Textbooks will be updated, future measurements will correct for void effects, and cosmology will move forward with renewed confidence in the standard model. If, on the other hand, the surveys show that the void cannot fully explain the tension, we'll know something deeper is wrong. That would open the door to more radical explanations, new physics, modifications to gravity, evolving dark energy, or possibilities we haven't even imagined yet. That outcome would be more disruptive, but potentially more revolutionary. It could lead to discoveries that reshape fundamental physics. Either way, we're on the verge of major progress. The combination of better observations, more sophisticated analysis methods, and larger data sets means we're entering a golden age for answering questions about cosmic structure and the expansion of the universe. The void is just one piece of this larger puzzle, but it's an important piece that ties into many other aspects of cosmology. Beyond the immediate scientific questions, the void also invites us to think about deeper issues. What does it mean to exist in a particular place in the universe? How does our environment shape not just our observations, but our very understanding of reality? These are questions that blend science and philosophy, and they don't have simple answers. Throughout history, humans have struggled to understand their relationship to the cosmos. Ancient cultures placed Earth at the center of creation, surrounded by celestial spheres. Copernicus displaced us from that central position, but for a long time we still thought we occupied a typical location. The cosmological principle enshrined this idea. We're not special, we're ordinary. What we see should be representative of the universe as a whole. The void complicates this picture. We might not be special in a cosmic sense. Voids are common, and many civilizations, if they exist, probably live in similar environments. But we're also not in the most typical location. We're in a region where the density is lower than average, and that affects what we observe. So in what sense are we ordinary? And in what sense are we unusual? The answer depends on how you frame the question. If you ask whether our location was selected by some special process or purpose, the answer is almost certainly no. We're here by chance, the result of random quantum fluctuations in the early universe that happened to create an underdense region in this part of space. There's no cosmic significance to our location beyond the fact that we happen to be here. But if you ask whether our location is typical in a statistical sense, the answer is less clear. Most of space by volume is in voids, so in that sense we're in a typical type of region. But most matter is in denser regions, and most galaxies are in filaments or clusters, so in that sense we're atypical. The question of whether we're typical doesn't have a single clear answer. It depends on what you mean by typical. This ambiguity is actually quite profound. It suggests that the concept of a typical location might not be well defined in a universe with hierarchical structure. There are common locations and rare locations, but there's no unique standard of comparison. This doesn't invalidate the cosmological principle. The universe is still homogeneous on sufficiently large scales, but it does add nuance to how we apply that principle. Let me return to the question I posed at the very beginning. What does it mean that we're falling through a hole in space 2 billion light-years wide? Now, after everything we've discussed, you can appreciate the layers of meaning in that statement. Literally, we're inside an underdense region of the cosmic web, moving through it at high velocity due to gravitational imbalances. The void affects our measurements, our observations, and potentially our understanding of cosmology. Metaphorically, we're inhabitants of a cosmic frontier, living on the edge of emptiness, looking out at a universe that's mostly void, with occasional concentrations of structure. Our perspective is shaped by this environment in ways we're only beginning to understand. The void is our home, our vantage point, the stage on which all of human history has played out. Philosophically, we're observers trying to understand a universe we're embedded in, recognizing that our observations are always colored by our location and perspective. The challenge of science is to see past these local effects, to discern universal truths. The void reminds us how difficult that challenge is, but also how progress is possible through careful observation and analysis. So what should you take away from all this? First, the universe is far more complex and structured than it might appear from casual observation. The cosmic web of filaments, clusters, and voids is the largest pattern in nature, stretching across billions of light years. We're part of that pattern, embedded in one of its largest features. Second, our local environment matters more than we used to think. For decades, cosmologists assumed our location was typical enough that local effects could be ignored. The void has taught us that this assumption needs to be examined more carefully. Where we are affects what we measure, and we need to account for that in our models and interpretations. Third, major scientific questions remain open. Despite enormous progress in cosmology over the past century, we still don't fully understand dark matter, dark energy, or the expansion rate of the universe. The void might help resolve some of these puzzles, or it might reveal that they're even deeper than we thought. Either way, the next decade promises major discoveries. Fourth, the process of science is ongoing and self-correcting. When observations disagree, we don't just throw up our hands. We investigate, propose hypotheses, test them, refine our understanding. The void hypothesis is an example of this process at work. Whether it ultimately proves correct or not, the investigation itself advances our knowledge. Fifth, there's profound beauty in understanding our place in the cosmos. Learning that we're in a void doesn't diminish us. It enriches our understanding of the universe and our relationship to it. Every discovery, even unsettling ones that challenge our assumptions, brings us closer to truth. Let me address one final time the question of whether we should be surprised to find ourselves in a void. I've mentioned anthropic reasoning several times, and it's worth being explicit about what that means. If there are physical reasons why intelligent observers tend to emerge in certain types of environments, then we shouldn't be surprised to find ourselves in such an environment, even if it's statistically rare for a random location. For example, if complex life requires stable conditions over billions of years, and such conditions are more common in moderately underdense regions like the outskirts of voids, then most observers would find themselves in such locations. The void wouldn't be special. It would be exactly where you'd expect to be if you're an observer. This reasoning is controversial because it can seem circular. We're in a void, therefore voids must be where observers tend to be. But done carefully, anthropic reasoning can be a legitimate tool for incorporating selection effects. The key is to have independent reasons for thinking certain environments favor observers rather than just reasoning backward from our observed location. In the case of voids, there are plausible physical arguments for why moderately underdense regions might favor complex life. Too dense, and there's too much radiation and too many galaxy interactions. Too empty, and there might not be enough heavy elements or enough nearby stars. The edges of voids, where we are, might be a Goldilocks zone. But this is speculative. We don't know enough about the conditions necessary for life to be confident in these arguments. They're interesting possibilities, but they're not established facts. As we learn more about exoplanets, the prevalence of life, and the conditions under which complexity emerges, we'll be better able to evaluate whether anthropic reasoning applies to the void question. Regardless of whether there are selection effects, the void exists and we're in it. That's an empirical fact that any theory has to account for. The question is whether it's surprising that we're in it, and that depends on assumptions about observers and the typical conditions for their emergence. These are deep questions without clear answers yet. Now let me close by returning to the emotional and existential dimensions of the void. There's something haunting about the idea of living in a cosmic desert, surrounded by emptiness. It can feel isolating, even lonely, to realize that most of the space around us contains almost nothing. The nearest major concentrations of galaxies are hundreds of millions of light years away. We're on the edge of a vast emptiness. But there's also something profound and awe-inspiring about it. The void is part of the largest structures in the universe. It's a consequence of the fundamental laws of physics playing out over cosmic time. It connects us to the Big Bang, to the quantum fluctuations that seeded all structure, to the slow work of gravity shaping the universe over billions of years. Being in a void means being part of that grand cosmic story. And we're not truly alone. We have our galaxy, our neighbors in the local group, the Laniakea supercluster. We have stars and planets, and the potential for life on worlds beyond Earth. We have each other, billions of humans sharing this cosmic journey. The void is vast, but it's not empty of meaning or connection. It's simply the stage on which our story unfolds. Looking up at the night sky, you're seeing the universe from inside this void. Every star, every galaxy, every photon of light has traveled through this region to reach your eyes. Your perspective is unique in time and space. No one else in history has seen exactly what you see from exactly where you are. That perspective is shaped by the void, by the cosmic web, by the entire history of the universe leading to this moment. That's what it means to live in a cosmic void. It means being part of something vastly larger than yourself, connected to the deepest patterns in nature, observing the universe from a particular vantage point that colors everything you see. It means being a conscious observer in a cosmos that might or might not have been expecting observers, trying to understand that cosmos from the inside. The void doesn't have all the answers, but it has helped us ask better questions. It's forced us to think more carefully about our assumptions, our methods, our place in the universe. It's reminded us that the cosmos is full of surprises, that our understanding is always provisional, and that there's always more to learn. As we look to the future, the void will continue to be an active area of research. New observations will refine our understanding. New theories will propose explanations. New generations of scientists will tackle questions we're only beginning to formulate. The story of the void is far from over. It's just beginning. So here's the challenge I'll leave you with. How does knowing you're in a cosmic void change your perspective on existence? Does it make the universe seem emptier or fuller? More hostile or more wondrous? Does it make you feel smaller or more connected to the cosmos? These questions don't have right answers. They're personal reflections that each person has to work through for themselves. But they're worth pondering. Science gives us facts about the universe, but we have to integrate those facts into our understanding of meaning and purpose. Learning that we're in a void is a scientific fact. What it means for your life, your worldview, your sense of place in the cosmos, that's something only you can determine. What I can say is this: the universe revealed by modern cosmology is far stranger and more magnificent than anyone imagined a century ago. We live in an expanding cosmos filled with dark matter and dark energy, structured into a cosmic web of filaments and voids, with a history stretching back 14 billion years to a hot, dense beginning. We're part of that story, observers and participants, trying to understand it all from our particular vantage point inside a 2 billion light-year void. That's astonishing. That's worth contemplating. That's worth sharing with others and discussing and exploring further. The void isn't just a scientific discovery, it's an invitation to think deeply about existence, perspective, and our relationship to the universe. I hope this journey through the cosmic void has given you a new appreciation for the complexity of the universe and the sophistication of the science that reveals it. The astronomers and cosmologists working on these questions are pushing the boundaries of human knowledge, using cutting-edge technology and brilliant theoretical insights to map structures billions of light-years across and understand processes spanning cosmic time. Their work matters because understanding the universe is part of what makes us human. We're the species that looks up at the sky and asks why. We're the species that builds telescopes and spacecraft and particle accelerators to find answers. We're the species that won't rest until we understand where we came from, where we are, and where we're going. The void is one piece of that larger quest for understanding. It's our cosmic neighborhood, our local environment, the region of space we call home. And now, after reading this, you know more about it than most people in history ever could have. You know you're falling through a hole in space 2 billion light-years wide. You know that scientists confirmed this in 2013. And now, unlike before, you've been told, in detail, with all the context and implications that discovery entails. So what will you do with this knowledge? Will you share it with others, sparking conversations about cosmic structure and our place in the universe? Will you follow the ongoing research, watching as new observations test the void hypothesis and potentially resolve the Hubble tension? Will you look at the night sky differently, more aware of the vast emptiness and the cosmic web beyond what you can see? Whatever you choose, you're now part of the story. You're an informed observer, aware of the void and what it means. That awareness connects you to the cutting edge of cosmology and to the deepest questions about existence. Welcome to the cosmic desert. Welcome to the void. Welcome to your place in the universe, now understood in ways previous generations could never have imagined. And welcome to the ongoing adventure of discovering what it all means. If you found this fascinating, leave a comment below. What aspect of the void surprised you most? Do you think it fully explains the Hubble tension? Or is there deeper physics at play? And here's the big question. Does living in a cosmic void make you feel more isolated or more connected to the universe? Share your thoughts. Subscribe for more deep dives into cosmic mysteries. And remember, you're not just on Earth. You're in a 2 billion light-year void, racing through space at 600,000 miles per hour, observing a universe that might be distorting its own appearance based on where you're standing. That's not a problem. That's the most profound adventure in human history. Thanks for taking this journey with me.